One more, and then we can put it all together. So the one that I want to do here is the I3, which is actually diagonal to point P. So first direction. So the direction, I'm going to use right-hand rule number 1. Here's my current. I'm going to put my thumb in the direction of the current, and I'm going to curl. Which way am I curling? Counterclockwise. Excellent. So I'm going to have a situation like this. And obviously you know that the field lines don't actually begin and terminate there. I'm just drawing a part of it. And then, so if you draw the actual field vector at point P, it's going to run perpendicular to the radius and tangent to the field line itself. That angle is 90 degrees, as dictated by the cross product in the via Savarlo. So here's the thing. Does everybody agree that I can draw a dashed line that passes through point P? That's the x-axis, you can think of it, and also the y-axis. They already told you what this angle is. That's actually given. What is that angle? 45 degrees. Does everybody agree with that statement? Everybody see that? That's 45. Why do I need that angle, though? Because I'm going to have to break up that vector into what? Into components. So does everybody agree that this angle would also be 45 degrees? Does everybody agree? Because the whole thing's got to be what? 90. Excellent. So now let's find out what that B3 is, magnitude. That's going to be mu naught I over 2 pi r. So 4 pi times 10 to the minus 7. What's my I there? 70? Yes. Divided by 2 pi times the radius, and the radius is 0.2 again. Yep. So that's 2, that's 10 to the minus 6. 7 times 10 to the minus 5 Tesla. But can I say that that's I hat, J hat, K hat, or is it a combination of I hat and J hat? It's a combination of I hat and J hat because this vector has a little bit of X and it's got a little bit of Y. So how do we actually compute its components? Well, very, very easily. You can say that B3 vector is going to be the magnitude, 7.0 times 10 to the minus 5 Tesla, times cosine of 45 degrees in the x direction. Does everybody agree that this would be for the x component? Minus. Why would the y component be minus? Does everybody agree the y component is down? In other words, this vector is in the fourth quadrant. In the fourth quadrant, x is positive and y is negative. Therefore, the y component should be negative. So minus the magnitude 7.0 times 10 to the minus 5 sine of 45 degrees in the j. Okay. So let's find out what our B3 is. Let's take a look. So B3, that's going to be 7.0 times 10 to the minus 5 times cosine of 45. So that's going to be 4.95 times 10 to the minus 5 Tesla in the I minus 4.95 times 10 to the minus 5 Tesla in the j. Okay, there's my B3. Does everybody see how I got the B3? So what would be the next step? Add all the i's together, that'll be your net I. Add all your j's together, that'll be your net j. Add all the k's together, that'll be your net k. And then to find the magnitude, square the x component squared, y component squared, plus the z component squared. Okay, but that part of it you can do, right? Yeah. All right, so we'll leave that part to you. All right, so take a look at number 4. So number 4, this one is rather complicated in the sense that there's a lot of stuff going on in this problem. So first off, you have a wire here, and you have a loop here with current flowing counterclockwise. 3 amps here, and in this one I have 8 amps. Okay, so now here's the thing. At the center of this loop, right here, you have an electron that is going to be projected. What does that mean, projected? It's shot. It's shot from point P towards the origin, so it's moving in the negative x direction. Will that electron feel a force when it is at point P? Well, let's think about it. If there was no electron there, and I wanted to calculate the magnetic field at P, would there be a non-zero magnetic field at point P? Would there be a magnetic field? And what is generating that magnetic field? This guy and this guy together. Would you agree? Now, that magnetic field will then act upon this moving electron when it is at point P. Remember, moving charges are affected by magnetic fields. So this is a two-stage type of problem where I first have to calculate the magnetic field generated by these two currents at point P. And then I have to figure out how much force that magnetic field is going to put on the electron that is actually at point P and it's moving. So let's first figure out the magnetic field generated by those two wires. Let's first find that. Okay, so first off I'm going to use superposition. So I'm going to do this guy first. Okay. So, current's coming out. Which way am I curling? Counterclockwise. So does everybody agree that that immediately means that my magnetic field should be up? Does everybody agree? Alright, that's B1. So let's find out what B1 is. B1 is going to be mu naught I. That's not a loop. That is a straight wire. And the magnetic field should be in the positive Y direction, which is symbolized with a positive J hat. Okay, so this is going to be mu naught, which is 4 pi times 10 to the minus 7. What's my I in that case? 8 amps divided by 2 pi times, and the radius, what's the radius? 0.25. So that's 2, that's 4, so that's 8 times 8, so that's 6.4 times 10 to the minus 6 Tesla. And that's going to be in the positive J direction. Okay, so does everybody see how we got this? Is everybody comfortable? Alright, so now I'm going to do the same thing, but this time for the loop. So first direction. For a loop, does it matter where I test it? No. So let's test it right here. I'm going to put my thumb in the direction of the current, which is this way. And then I'm going to curl my fingers like this. So when I'm below the wire, it's, or below the loop, it's in. And when I'm above, when I'm inside the loop, it's out. So that means it's going to be in on the outside of here and out on the inside of here. Does everybody see how we got that? Now you could have tested it here. Watch. Thumb is pointing in the direction of the current. Current goes this way, right? So thumb is in the direction of the current curl. So when I'm on this side, it's in. And when I'm inside, it's out. Okay. All right. So pointing out means positive what direction? Positive K. Excellent. So that B2, that's going to be mu naught I over 2 pi R in the K hat. Something's incorrect. Who can spot it? There's no pi in there, right? This is a loop. This is not a wire. This is not a long straight wire. This is a loop. So it looks like this. So mu naught is 4 pi times 10 to the minus 7. How much current is flowing there? 3 amps. Divided by 2 times the radius. And what's the radius of this guy? How much? 10 centimeters? Okay, so that's 0.1, basically. So that's going to be 2 pi. So 6 pi. So 6 times 3.14. 1.8 times 10 to the minus 5? Yep. Okay. So 1.8 times 10 to the minus 5 Tesla. And that's going to be in the K hat direction. Okay, so does everybody see how we got these two fields? So now if I want the net field, what would I do using superposition? I would add them. Can I just add their magnitudes? Can I just add 6.4 times 10 to the minus 6 plus 1.8 times 10 to the minus 5? Can I do that? No, because they're in different directions. So I add them vectorially. I say that B net is equal to 6.4, nothing in the x direction, 6.4 times 10 to the minus 6 Tesla in the j direction, plus 1.8 times 10 to the minus 5 Tesla in the k hat direction. That's my net field. Does everybody agree with that statement? Yes. Okay, so that's the first part of the problem. Now, I actually have an electron that is projected from point P towards the origin, moving in the next negative x direction. So the force on a moving charge due to an externally applied magnetic field, that's called the Lorentz force. And the Lorentz force, remember the equation for it is Q times the velocity vector cross product with the magnetic field vector. And since this is using the net field, that's going to give me the net magnetic force on that charge. So, first off, this is not magnitude. Does everybody agree that this is the full equation without the magnitude? Everybody agree? So, it's an electron. So, do I have to include the negative sign if this is not a magnitude equation? It's not the magnitude of F equals this, right? So I have to include the negative sign for the electron charge. So that's 1.60 times 10 to the minus 19 coulombs. That's the charge of an electron. Okay. Velocity. Does everybody agree that the velocity vector, they actually told me, first of all, it's pointing in the negative x direction. So does everybody agree that that would be negative I hat? So it would be the speed, which was, how much? 3.0 times 10 to the 6 meters per second in the I hat direction. Negative. Because it's pointing, remember, it's moving in the negative x direction. Cross product with the net magnetic field that we just calculated. 6.4 times 10 to the minus 6 Tesla into J plus 1.8 times 10 to the minus 5 Tesla into K. Okay, does everybody see that? How we set it up? Now, here's the cool thing. You can actually go ahead and distribute this. So I cross product with J. What does I cross product with J give me? K. And I cross product with K gives me negative J. Okay, so let's do this guy first. I cross J. So that's going to give me. Does everybody agree, first of all, these two negatives cancel? Does everybody agree? Yeah. Okay, so the first one is going to give me 1.6 times 10 to the minus 19 times 3 times 10 to the 6th times that scalar, 6.4 times 10 to the minus 6. And I cross J is K, if you remember, from cross products. So you don't have to do this with a matrix. Okay? The determinant, remember the determinant 3 by 3? You don't have to do that. It's a lot easier than that. So I cross J is K. Alright, now this guy, this multiplied with that, so multiply the scalars first. So 1.60 times 10 to the minus 19 times 3 times 10 to the 6th times 1.8 times 10 to the minus 5. And now I cross product with K is negative J. So I'm going to put the negative out here, and that's negative J. Okay, so does everybody see how we got this? Okay, so now let's plug this into the calculator. Let's plug this guy into the calculator, let's plug this guy into the calculator. So let's take a look. So let's look at that first number. So that's going to be 1.60 times 10 to the minus 19 times 3 times 10 to the 6th times 6.4 times 10 to the minus 6. So I get 3.072 times 10 to the minus 18 newtons this time, because now it's a force, not a magnetic field. This is the force that the magnetic field is putting on the charge. So newtons in the K hat direction, that's the positive Z direction. And then minus, now I'm going to get the other guy, 1.60 times 10 to the minus 19 times 3 times 10 to the 6th times 1.8 times 10 to the minus 5. So minus 8.64 times 10 to the minus 18 newtons in the J hat direction. So this will be F net. And of course, technically speaking, you have to rearrange the order, right? Because the J comes before the K. Now, it's asking for the magnitude of the net force. How would I find the magnitude of the net force?
Square root.
Yep, so square root of the x component squared, which is 0, plus the y component squared, which is 8.64 times 10 to the minus 18 squared, plus the z component squared. Remember, because it's 3D. So that would give me my final answer. So I'm going to square the y component plus the x component. And then I'm going to square root that. So I'm getting 9.17 times 10 to the minus 18. And what are the units? Since it's a force, newtons. Excellent. All right, so does everybody see how we got this one? Is everybody good? Can I clarify any of the steps for anybody?